Hello everyone and welcome to MV Tutors. I'm Solo and I'll be looking at the Gauteng June exam paper written recently. We're looking at physical sciences today, right? Paper 1. Okay, physics. So without wasting any time, let's just go ahead. Please don't forget to like our videos and subscribe to our channel. Thank you for those who keep subscribing. Thank you for those who keep commenting, giving us feedback, um, errors that we've made that need fixing. We're not perfect, guys. We're here to serve you. So help us to best serve you by commenting, liking, subscribing, correcting, critiquing, and for the good messages as well. Thank you for those. Whenever I open up a message that I see, I'm like, oh my gosh, is it another complaint? And it's weird that we always focus on the little complaints. Like you get 100 great messages, and that those two comments are like, so in your mind you're like, there were two comments. I missed this. Oh my word. Rip is ruined. But it's all good. Criticism helps us to stay on our toes and to perform perform better. All right, so now that we're done with those intros, let us do this. Let me just make this a bit bigger and let's start the question. Okay, now I've lost my cursor. There it is. Okay, so question 1, multiple choice. Here you can bank marks, but you can also lose them because sometimes the options are quite similar. So now it says a box is shown resting on the ground, all right? Newton's third law implies that four forces of equal magnitude are involved, right? So now these forces are labeled P, Q, R, and S. Forces P and Q act on the box, all right? One is a contact force, the other is a gravitational force. Then we have forces R and S that act on the earth, okay? And those ones will be your non-contact forces. So for clarity, the forces are shown slightly separated. So we can see on the box, there's a P, Q, then R and S. So which statement about the forces is correct? A, force P is equal and opposite to force Q? Yes. And both are forces of contact? No. Only P is a force of contact, your normal force, but Q is a gravitational force. Force Q is equal and opposite to force P. And both are gravitational forces? No. We've already established which one is gravitational and which one is contact, right? Which one is your normal force. C, force R is equal and opposite to force S. And both are forces of contact? Nuh-uh. D, force S is equal and opposite to force Q. Yes. And both are gravitational forces. Yes, that is true. Okay, they are not contact forces in this case, they are gravitational forces. All right, now 1.2. Okay, so a child on a sledge slides down a hill with acceleration A. The hill makes an angle theta with the horizontal. The total mass of the child and the sledge is m. Okay, so they've combined it. The acceleration of free fall is g. Now, the frictional force is represented by, so at this point, I would recommend you draw yourself a free body diagram because how can you just look unless if, you are a seer. So you have force of gravity always acting downwards. Then you have your contact force, the normal force. You have your, if you put theta over there, you can get your force of gravity in its components. Remember the force of gravity is Fg. Okay, and if you put it in its components, it's a different color. You're gonna get Fg cos, because here it's adjacent to the angle. So cos theta, and then there you have Fg, let me just say Mg. No, it's much better to say Mg because I see that's what's in our answer. So Mg cos theta, then you have Mg sine theta, all right? And then there's friction. Okay, I mean, yeah, this surface, they didn't tell us that it's frictionless. So, and after all, we are looking for the friction force. frictional force. So friction is always acting in the opposite direction. The fact that this person is moving downwards means that the friction force is not that big. Okay, so frictional force is represented by, all right, in this case, we can see that the frictional force is actually, frictional force, yeah, I'm just going to say, I can just say FK, actually. Yeah, so the frictional force plus, no. If I add the forces in the x direction, minus Fk plus mg sine theta is equal to mass times acceleration. And in this case, they told us that the acceleration of free fall g. Okay, so we actually have mg instead of ma. All right. And now if I take this to the other side and this side, I'm going to have mg sine theta minus mg is equal to fk, but I want fk as the subject of the formula. So I'm going to take mg out as, okay, in my answer, I see they left acceleration as is. Okay, let me leave it as is also here. Okay, it's all good. It's always good to look in your answer what is actually there before you get carried away like I just did. So if I take out the mass as the common factor, I'm left with gravitational acceleration sine theta minus the acceleration in the x direction. Okay, and we then can see from our answer, we have sine theta minus a, so 1.2 would be c. Okay, and then moving right along. Ooh, this is gonna be a long session. All right, multiple choice does take time if you want to do it properly. Now, a small steel ball falls freely. So it falls, it wasn't dropped. Okay, it was dropped. It wasn't thrown. Okay, so there isn't like an initial velocity. It was falling. Okay, under gravity. All right, after being released from rest. Yes, from rest. I was waiting for that. So it was dropped. Okay, it fell. It wasn't thrown. So which graph best represents the variation of the height h of the ball with time t when using the ground as a reference? If I think about it logically, I have my ground there, and this is my steel ball, and it falls, right? So just gonna go straight down. But the moment I introduce time, it does something like this. All right. And so in this case, we will get B, because if I look at A, it's not a straight line. Guys, your displacement versus time graph is not a straight line. It's more of your parabola because the motion is parabolic, right? What's the actual word? It's a projectile. Okay, so with projectile motion, you do get the parabolic shape. So if I look at B versus C versus D, B has to take the prize. C and D, no. Yeah, let's just go with B. All right, and then 1.4. So it says if air resistance is negligible, okay, we don't consider it, the total mechanical energy of a free falling body, remember EMEC, which is your mechanical energy, is equal to your potential energy plus your kinetic energy. Okay, and if you are going to, let's say, free falling body, if you're gonna, at this point before the body falls, you have your maximum potential energy and your kinetic energy is 0. Okay, but as it falls, your potential energy reduces, your kinetic energy increases, and then by the time you reach the ground, your kinetic energy would be its maximum, whereas your potential energy would be 0. Okay, so throughout this, the decrease in your potential energy is your increase in kinetic energy. So therefore, the total mechanical energy of a free falling body free falling body should remain constant. Okay, so it doesn't increase, it doesn't decrease, it does not become zero, it has to remain constant. Okay, so D is the right answer for 1.4. Forgot to add pages to this. Let's add them pages and continue at the top. So going to 1.5. So now my sheet is like, yeah, disorganized. It's fine. The diagram below shows two identical spheres, X and Y. So they're identical, meaning they have the same mass, the same shape, yeah, the same density, everything. So initially X moves with speed V directly towards Y, while Y is stationary. The spheres collide elastically. Remember, elastic collision means that the kinetic, rather the sum of the kinetic energy before is equal to the sum of the kinetic energy afterwards. So now, what happens? Okay, so the following occurs. So for option A, X stops and Y moves with a speed V to the right. B, X moves with a speed V to the left. So basically it rebounds, okay? And then Y remains stationary. I doubt that would happen. There has to be a transfer of energy with that contact. I mean, imagine someone comes, you're there stationary, and they bump against you. They will not bounce back. You will do something. So I don't think B is the right answer. C, X moves with a speed half to the left and Y moves with a speed half to the right. D, X moves with the speed half to the right and Y moves with the speed half to the right. So both go that way? No. When I think about this question and how to answer it, by the way, I'm going to go with A, that X stops while Y moves with the speed V to the right. Think about that pendulum. Let me just draw the string. You have that. And then you have all these other, I don't know what they call it. I forgot the name. It's Newton's something. Okay, for those who remember what the name is, please help a sister out. Okay, so with that, so now as soon as this comes with its own velocity v and it hits there, what happens is that force moves to the next and the next and the next and the next until it reaches the end, and then you get it doing that, right? While this one goes back to position. So it does, you know, that kind of thing. Ooh, not knowing the terms at this point in time. Sorry for my lack of terminology right now. English is failing me. Not that I would know it in Tswana, but yes. So it would go with this velocity and then it's transferred to the last pendulum, and then it goes up and then comes up back again. Okay, so that's what I'm thinking about when I'm answering this question, and hence I'm saying that X will stop, right, while Y moves with speed V to the right, because this is elastic. Okay, and then Y will come back to the left, will stop, and then X continues with the same velocity. Okay, 1.6, so we are past halfway. Now it says the direction of an object's momentum is always the same as the direction of the object's. Now momentum, remember the formula is mass times velocity, and velocity has direction, right? Because mass is a scalar. Yeah. So now momentum, the object's momentum is always the same as the direction of the object's velocity. I would go with it. B, weight. Remember, weight is not mass. Weight is mass times gravitational acceleration. So it's not there in the equation. Inertia, potential energy, I would really go with A, which is velocity. Okay. Now what did I do? Okay. So yes, A would be the correct answer in this case. And then 1.7. A satellite orbits Earth at point X. Okay, so there is the satellite. The gravitational force on X is a quarter of the gravitational force it experiences on the surface of the Earth. Okay, so if the radius of the Earth is r, then the height of the satellite above the surface of the Earth will be, okay, so what comes to mind is the equation, okay, force of gravity, gravitational force is equal to that constant, big G, and then mass of one, mass of the other over r squared. Okay, this time let's just use a big R because that's what we're being referenced to. And now they tell us that the gravitational force on X is a quarter of that experienced on Earth. So let's just say this is what's happening on Earth. Now, experienced by X, it's really just going to be a quarter of G mass 1 mass 2 R squared. Okay, if I write it all under one division sign, okay, I have 4 R squared. Okay, so now it says the height of the satellite above the surface of the Earth will be 4R. No, it's only R that is squared. Okay, 4 is just the number before R squared. Okay, so we didn't change the radius at all. And then B, 2R, no. CR, yeah, R remains as it is. The radius remains as it is. Nothing changed. If they said it's a quarter of the radius, then you would have applied a quarter and then squared everything. Okay, but in this case, it's just a quarter of the force of gravitation. So in this case, C is the correct answer. Okay, because R didn't change at all. It's just the coefficient in front of R squared, not R. So C is the correct answer. D, half R, no. Okay, and then 1.8. The warning siren on an ambulance has a frequency of 600 hertz. All right, so if you are inside the ambulance, you always hear 600 hertz. The speed of sound is 330 meters per second in air. The ambulance is traveling at a constant velocity of 25 meters per second towards an observer. Okay, so now we have the initial position of the ambulance and then the observer. So the ambulance is approaching the observer, and remember with Doppler effect, as it approaches, the sound waves actually become less and less and less, but the sound intensifies, the frequency actually increases, okay, in that direction. And then as it leaves, final position of the ambulance, well, the waves start getting bigger again, so the frequency is actually much less. All right, so now it says, which graph illustrates the change in observed frequency? All right, so is it a constant decline that you start hearing it as a loud sound and then over time it just gets less until you don't hear it any longer? Or does it start increasing even after they leave? Think about it practically. If something approaches you, the sound becomes intense, and then once it leaves, it becomes less. So neither of these, actually A and B, would represent it quite well. It's not like this. It's not linear like that. Okay. Now, between C and D, what happens? Is it increased at the beginning and then decreased at the end? Or is it decreased at the beginning and increased at the end? I would go with C, okay? Simply by me just showing you that as it approaches the listener, the sound waves actually become less, and wavelength as well as frequency, they are inversely proportional. So when one reduces, the other increases. Okay, so as it approaches, you'll hear a higher frequency, but as it leaves, the frequency will start decreasing. So C would be the correct answer for 1.8. Okay, and then let's go over to 1.9. We're almost there. Okay, I thought we were going to take forever with question 1, but we're not. So it says, which diagram below best represents the electric field pattern between 2 point charges of equal magnitude and opposite signs? let's just draw it out for ourselves. So we have the positive and we have the negative. Okay, so where does the magnetic lines, how do they flow? Do they flow from negative to positive or positive to negative? So when it comes to the negative, we can actually have something like this. Okay, no, what am I doing? Yes, something like that. No, these ones, I'm gonna do this. Yes, because they are attracted to each other. Opposites attract, equal repel. So they actually do that. My goodness. Okay. And then we have this on the other side. Okay. Now, the lines, the magnetic field lines, they actually, for the negative, it goes inwards. Okay. But for the positive, it actually goes outside. Okay, and so where do we see that pattern? So A and C, no. Yeah, no A and C, right? A and C is not cutting it because that's where we have, it plots the shape of those that have equal sign and not opposite sign. But B and D, we can definitely look at. And if we look closely, so B has the magnetic field lines going in on the positive side, which is incorrect. Okay, they should be going in on the negative side. So actually D should be your answer and not B. All right. So 1.9 is D. And then finally 1.10, we are there. Which of the following represents the correct units for electric field strength? So electric field strength, if you forgot the formula, I suggest, if you forget any formula, please go to the formula sheet. You can still use it for question 1, just to make sure that you have the right equations and you understand it correctly. So electric field strength is E KQR squared, but that formula actually comes from force over Q. You know that force is actually equal to K and Q1, Q2, and R squared, blah, blah, blah. So yeah, this is where it originates from. And the unit for force is Newton, right? So I'm going to put it there. And the unit for charge is Coulomb. So going up again, finally finishing this question. A, T, no. B, Newton Coulomb. Yes, if we bring the Coulomb up there, it'll be Newton Coulomb. J, no. Joules per Coulomb, no. D, no. So we're gonna go with B in this case for 1.10. And that, yeah, that closes the chapter for question 1 in this physics paper. I hope this helps prepare for prelims. But what I would suggest for prelims though is for you to go through past prelim papers, okay? Because prelim papers are more challenging than the normal November exam and so forth. So there's a good place to start, but also address the past prelim papers, okay? But that's it from me. See you again next time. Hello everyone and welcome back to MV Tutors. I'm Selena. I'll be looking at question 2 with you guys for our physics paper. Alright, don't forget to like our videos and subscribe to our channel. And I hope the prelim preps are underway and going well. Okay, so now it says a log of mass m kilograms is pulled up a slope by a light, non-elastic wire of negligible mass, attached to a motor as shown in the diagram below. Okay, now the angle that the slope makes with the horizontal is 12 degrees. The kinetic coefficient of friction between the log and the surface is 0.3. That's like mu k, 0.3. Yeah, our theta there is 12 degrees. The tension in the wire is 1,570 Newton, while the log moves up the slope with a constant velocity. All right, so tension force, we have it there, it's 1570 Newton. Constant velocity means that we have zero acceleration. Okay, now 2.1. I wonder when it comes to definitions, I'm just going to say it, I'm not going to write it. State Newton's first law in words. Okay, so Newton 1, for those who are not good at cramming, remember it just says that when you have a body in a state where it's at rest or it's moving at constant velocity, it will remain at rest or it will remain moving at constant velocity unless an external resultant force that is not equal to 0 acts on it. Okay, so you're there minding your own business, driving on the highway, keeping to 80 or 100 kilometers per hour, and you just, consistently driving. You've put it on speed. Is it cruise control? Speed cruise control. Yeah. And then motofela out of nowhere just comes, with the resultant force, just crashes into you. So you will continue moving at that velocity, okay, 100 kilometers per hour, unless someone who's not focusing or who's in a rush comes and bumps you. That's Newton 1. Now, 2.2. Draw a labeled free body diagram to show all the forces acting on the log. Okay, so this is like your slope. That's your log. The easiest one to begin with is your force of gravity. Okay, it's always going down. Okay, and then acting perpendicular to it is your normal force, your contact force. Some just put an N. I don't know. Do what your teacher tells you, because they're the ones who will be marking your script. Then you have a force of tension. Okay, we have been given what that is. And then, is there friction? Yes, they told us about the coefficient of friction. So if this thing is moving upward, pulled up the slope, friction will act in the opposite direction. Okay, and the fact that it is moving upwards means that the leg of friction must be shorter. Again, with that, some people don't really take that into consideration, the lengths of these arrows. So yeah, maybe it's not that important. So how many marks is 4 marks? They like giving marks according to how many forces you represent. So you can either leave it there, or you could have chosen to take your force of gravity and put it in its components. Let me use a different color for that. All right, you're not going to get extra marks for putting it in its components unless if from the get-go you do not put the gravitational force going down. So if this is your angle over there, which is 12, so you're going to have FG cos 12 degrees because this is the adjacent side. And then here you're going to have, I don't know how long I should make that arm. So FG sine 12 degrees, okay? And that's basically going down. But yeah, with the original 4 we drew, you should be fine. And 2.3, calculate the mass of the log. Okay, so what do we have? I would rather, because we don't have mass, I wouldn't want to sum up the forces in the y direction. I would rather sum up the forces in the x direction. So we have tension minus friction force minus Fg sine 12 degrees, and that's equal to mass times acceleration. Okay, so the equation comes from sum of forces in the x equal to ma, not 0. But in this case, yes, it's 0 because acceleration is 0. All right, so the tension they have given it to us is 1570. Force of friction, remember that's equal to your normal force multiplied by your coefficient. And your normal force is mass times gravitation. Ooh, be careful. Be careful. This is what Fm normal force is equal to. It's equal to Fg cos 12. Okay, so Fg is the same as mg actually. So yeah, mg cos 12 degrees times our coefficient there, which we wrote at 0.3. Okay, so let's put everything together. What are we looking for? The mass. It's always good to go back and check what are we looking for exactly before you go too far in. And then we have cos 12 degrees, and all of this is multiplied by 0.3, and then minus fg sine 12. So again, m times 9.8 times sine 12 degrees, and it's equal to ma. The acceleration is 0, thank God, or else we would have had two unknowns. We would need another equation, and oh my goodness. All right, so we have 1570. Now let us see. Let's just put everything into the calculator. So we have 9.8 times cos 12 times 0.3 decimals. So we have 2.88 m minus, I'm just going to save this, store it as a, okay. Then we have 9.8 multiplied by sine 12 degrees, and that is 2.04 m. I'm going to store that as, what was the previous one? C. Let me check. No, B is 0. So A is what I stored the first one as, and C the second one. All right, and that is equal to 0. So I'm going to take both of these to the other side. So I have 1570 is equal to 2.88. So C, or A plus C, that's equal to 4.91 m. So therefore m is equal to 1570 divided by 4.91. That looks too big. Yeah, that is like, wow, okay. But wait, it's a log. Yeah, but still, that's like a lot. 300 and what? Kilograms? That's a heavy log. Okay, let's go back to the calculator. It is what it is. 319.54. That's a lot. That's big. That's a heavy log. Or maybe I'm just looking at the picture and it looks like something that would weigh I don't know, like 50 kilograms, not even 50, 20. But yeah, it must be a big one. Hence, probably they needed to use a motor to lift it up. Okay, that makes sense. If I factor in the motor portion of it, it is what it is. Okay, now 2.4. So it says the angle of the slope is increased by 14 degrees. All right, what effect does that have? So now I'm exaggerating. This was before with your 12, and now we're like here with 14. Obviously not, but for the purposes of understanding what's going on, we gotta exaggerate things a bit. So now, identify the effect of this increased angle on each of the following. Write only increase, decrease, or remains the same. So what happens to the kinetic coefficient of friction between the log and the surface? Will it change? No, it won't. Remember, the coefficient of friction is dependent on the type of material that you have, or type of surface. Let me not say material. So if the surface is still the same, the coefficient of kinetic friction should be the same. All right, so there it remains the same. We're not expecting any change. Now when it comes to 2.4.2, let's see what would happen to the frictional force. Okay, remember this thing is more steeper, né? And we are pulling it up. All right. Sorry. If we have our force of gravity there, and this is our Fg cos theta, and that's our Fg sine theta. the steeper this becomes. So if it's like this, you'll have this, that, and that. But now when it becomes steeper, this becomes less, okay? So your FG sine theta decreases. And what happens then to your friction? Will it increase? Will it decrease? What are you expecting? So your frictional force in this case, remember your normal force, it actually depends on Fg cos theta. So when it became, this leg. Okay. When you now increase the slope, Fg remains the same, but what happens? You have increased your theta, okay? So now this remains the same. Fg remains the same, but cos theta has increased. So we are expecting our friction force to actually increase in this case. And I hope that makes sense. And I'm saying I hope it makes sense because if there wasn't any tension force, right, let's say there's no tension. All right, so in this case, there's tension. And the tension is what it is. So if there's no tension, your log wants to move down, right? And friction is acting in that direction. So the flatter it is, the higher the friction, but the steeper it is, the lower the friction. So in this case, without a tension force, your friction force will definitely get lower when your log is going downwards. Okay, but with this tension force, let's see. So you have tension, and that tension, it remains as is, doesn't it? Yeah, it remains as 1570. And this friction force should increase because your angle has increased. Okay, I'm at war with this question. Tell me what you think. I say it increases. Okay, if there wasn't any tension strain there, it would decrease. But what do you say? Yeah, if you have an opposing view, please let me know so that we can conclude this matter. All right, so now it says the wire snaps. And the log slides down the slope until it stops. So now friction has changed direction, right? We have gravitational force taking the log downward, but we have friction force opposing. Now it says, give a reason why this cannot be seen as free fall or projectile motion. Okay, so in this case, it cannot be seen as free fall because free fall by definition is when only gravitational force acts on the projectile, on the body. In this case, we have both gravitational force as well as friction force acting on this log. So it cannot be seen as a free fall. Okay, so because of this, cannot be free fall. Okay, and that sums it up for question 2.5. Hello, and welcome back to MV Tutors. We're looking at question 3 of our physics paper. And don't forget to like our videos, subscribe to our channel, turn on the notification bell so that you're notified when we post a video and you're up to date. All right, so let's get right to it. A soft ball is thrown vertically downwards. Okay, so it is thrown. There is an initial velocity that has been given to us. It's 8.4 meters per second. So it is thrown vertically downwards toward the ground, where after it bounces back up as illustrated in the sketch below. Okay, great. Now when the ball reaches point A, it has a speed of 8.4. Okay, so we don't know the initial velocity actually. We just know that at 5 meters above ground, the velocity is 8.4 meters per second. The height of A is 5 meters above the ground. The ball hits the ground and bounces up to a maximum height at position B. We don't know what that maximum height is. Now assume that air resistance is negligible. All right. Before you even go far with these questions, you're going to calculate some velocity. I think decide for yourself which one is positive. Is downwards positive or upwards positive? I think I will go with downwards being positive. Okay. As a result, I know that my G will always be positive 9.8 meters per second. Okay. And this A, velocity at A, is positive 8.4 meters. Ooh, did I say G is per meter squared? This is per meter. Meters per second. What am I saying? G is meters per second squared, and velocity is meters per second, not per meter. My goodness. Okay. So now 3.1, explain the term projectile motion. Well, basically, it's a body or a projectile that only has the gravitational force acting on it. That's how I would explain it. Yeah. And then 3.2, calculate the speed of the ball as it hits the ground. Okay, so from A to ground, we have 5 meters. We know that the velocity here is 8.4 meters per second. So I'm going to take that as my initial velocity, and then my final velocity is something. This is what I'm trying to calculate. And I'm going to go to my equations of motion so that I can see which formula to use. Cool. So what do I have? I have delta y, right? So I'm going to look at, I don't want to take an equation that has time in it. I don't want to do that to myself. So the equation that would work best if I have initial velocity and final velocity. How? All of them have time. Okay. Uh-huh. Oh, I think they wrote this incorrectly. 2a delta a. I think that should be delta y. I hope. Oh my word. This formula sheet. Now I have trust issues. Let me just see if I can get a formula sheet quickly, and I'll be back. Okay, so I found a formula sheet which has the formula with delta y without time. Yes. Okay, so there it is. So we have velocity, final velocity squared is equal to initial velocity squared plus 2 times acceleration. In this case, we have gravitational acceleration and delta y. Whew. Okay, now let's go back to the physics paper that we are busy with. So they made an error there. I hope the kids informed the teachers, or the teachers came and said, hey kids, change this. So we're looking for the final velocity. We have the initial velocity, which is 8.4 squared. And then we have 2 times 9.8. Remember, it's positive because we took downwards as positive. And then delta y would be 5. Okay, so velocity, final velocity would be the root of 8.4 squared. 2 times 9.8 times 5. Actually, 2 times 5 is 10. 10 times 9.8 should be 98. But in the calculator, I'm putting things as it is because, wow, you cannot just trust anything. Hey, put things as they are. 8.4 squared plus 2 times 9.8 times 5. You see, when a calculator doesn't put the square root over the entire thing, I start having trust issues because I'm thinking, where is the square root applicable? Okay, so the final velocity is 12.98. Now, this is where after getting an answer, you critique it and you ask yourself, does it make sense? Remember, if we've started at 8.4, we're expecting our velocity at the ground to be at the maximum. It is increasing as you go down. Okay, It's not the same, and it doesn't decrease, it increases. So 12 is higher than 8. So I would be confident in my answer. And that's 3 marks. So 3.3, show by calculation that the time for the ball to reach the ground is 0.47. Okay, now we can go to the equations, where there's time involved. All right, so I'm going to go to the equation where I have my distance and I have my initial velocity. Why? What if I calculated my final velocity incorrectly? I don't want to carry on with the wrong answer. Okay, so I'm going to go then with delta y is equal to initial velocity times time. The only boring thing about this is now you have a quadratic formula here. The t squared. So we have 5 over here. Initial velocity is 8,4. I'm just going to drop the delta. And then I have 0,5 times 9,8. And I have t squared. Okay. Yeah, it's not nice dealing with squares, but I'd rather be safe than sorry. Because like I said, I don't want to use the final velocity that I got previously just in case it's incorrect. All right, so 0,5 times 9,8 is 4,9. So I'm going to do this 4,9 t squared plus 8,4 t minus 5. Okay, so this is where you use your quadratic formula. Okay, I am going to use my special calculator and see if I can solve for this equation. But yes, you use the quadratic formula. Okay, now I feel bad for not using the quadratic formula because these calculators are really not allowed for you guys because they can solve equations. So 0,47 seconds, or we have a negative, so that cannot be. T is equal to negative 2,18 seconds. No, that can't be. Okay, let's just say I use the quadratic formula. I would say x, remember the quadratic formula would be t is equal to negative 8,4 plus minus 8,4 squared minus 4a c, and all of that is under a square root, and we're going to divide by 2 times a. Okay, that was not so bad. That was actually quite quick. I should have just gone with it in the first place, but for those who have these special calculators, use them to your disposal. Do not waste time. I'm just being considerate here because it would be unfair not to present this as well. Okay, we have negative 5. I'm an engineer, guys. We want to get things done quick but accurate. Okay, so there is the negative answer. No, that's the 0,47, right? And then the negative portion, negative 2,18, which is not what we're going to use. All right. So yes, so they did say we should prove, right? Yes, 0,47 seconds. I've shown it. Great. Now 3,4. The ball bounces vertically upwards with a speed of 4,2 meters per second as it leaves the ground. Remember, it hit the ground at 12, guys. 12,98, almost 30 meters per second, and now it's bouncing off with 4. What happened to the rest of the velocity? Okay, so that shows that this soft ball, they told us it's a soft ball, right? This soft ball transferred energy. Okay, it wasn't an elastic collision, it was an inelastic collision. Okay, so now the time the ball is in contact with the ground is 0,2 seconds. That's quite long. Okay, if you think about it, it is a little bit long. So hence that's where the velocities got lost. They got in contact with the ground. There was heat transfer, there was sound there was sound, energy converted from kinetic to sound, kinetic to heat, and the force from the ball to the ground to the ball, blah blah blah. So that's where it went. Now it says 3.4.1. What is the magnitude and direction of the acceleration of the ball at point B? Remember, this is a projectile, okay? So nothing really acts on it except what? Gravitational acceleration. So what is the magnitude and direction of the acceleration of the ball at point B? It's still going to be, so G, acceleration, let me just say A. Acceleration is going to be 9.8 meters per second. And the direction is always down, guys. Gravity downwards doesn't really act upwards. So 3.4.1, it's going to be downwards. Okay, now let's go over to 3.4.2. Calculate the maximum height that the ball reaches after the first bounce of the ball. So they told us that it bounces off with a speed of 4.2. So the initial velocity is 4.2 meters per second. And a final velocity, no, we know our final velocity, if it reaches its maximum height, that will be 0. Okay. And what else do we know? We don't know the height. We're looking for the height. Yes, we're looking for the height. So which equation would be applicable? Yeah, we can use final velocity squared is equal to initial velocity squared plus 2 times g delta y. So this initial velocity, we chose upwards as positive, we chose downwards as positive, so this will be negative. No? Well, final velocity is just, it is what it is. It's 0. So, but anyway, the negative will be taken out by the squared. Plus 2 upwards is, yes, so downwards is positive. So we're still keeping to 9.8. And then what happens to this y? This y we're going to calculate. Let's just see what happens. But we're going to get a negative, which, because of the way we chose that downwards is positive, this thing is going upwards. So we're expecting y to be negative because downwards for us is positive. Okay, I'm just putting it out there so that you don't get surprised when we start getting negative answers. So we're going to then say negative 4.2 squared divided by 2 times 9.8 is equal to y. So y is equal to negative what? But because this is the height that we are referring to, ultimately you're going to have to say your answer is positive. The negative is really because of the convention that we chose. Okay, so we have negative and then negative 4.2 squared divided by 2 times 9.8 and that is 0.9. So negative 0.9 meters. But like I said, it is 0.9 meters. That is the height. Let's just go back to the question. That is the maximum height that the ball reaches after the first bounce off the floor. Okay, now we are going to 3.4.3, sketching. Yay, or not so yay for some. 3.4.3. Now sketch a velocity time graph of the motion from the moment that the ball passes A until it reaches position B. Okay, remember we took downwards as positive. So we have, it started off with 8.4. Okay, this is your velocity measured in meters per second. And this is your time measured in seconds. So we started at 8.4, right? And, oh, actually, let me do this. Let me sketch this 8.4 a bit lower. So let's just say this is 8.4. And then as it reached the ground, we were at 12, something. 12,98. Okay, 12,98. And when did we reach 12,98? I think we said, did we calculate the time? 0,47 seconds. Show by calculation, the time to reach the ground, 0,4 seconds. So I'm just going to say this is 0,47. So we started there at time 0, and we were here at 0,4 seconds. We were at 12. Okay, so this is position A. This is the ground. Okay, and then, so yeah, there, ground, and then we spent some time on the floor, right? They gave us the time there, it was 0,2 seconds. So 0,47 plus 0,2 is 0,67. Okay, so this is where you get your dotted line, the time spent on the ground. And then now it went upwards with a speed of 4,2. So now we are here, negative 4,2, because downwards for us is positive. So we started, let's do this. This 4,2 is here. So our dotted line actually is like that. So this thing went up and reached 0 at its maximum height, which is at B. And you must make sure that these lines are parallel, because the gradient of a velocity time graph is acceleration. Remember? Sorry about that. Delta V over delta T. So the gradient is acceleration. So it must be 9,81. So the lines must be parallel. Don't make them any other way. So that is where B is. Okay, here we're still at the ground. All right. So what do they want to see? I've been sketching the velocity of the ball at A, 8,4. Velocity of the ball as it hits the ground, 12,98. Time taken for the ball to reach the ground and leave the ground, that's that 0,2 seconds. The velocity at the maximum height at point B, that's 0. Okay, so that is how you would sketch the graph. I need some water. Are we done? Oh, we still need to go. Okay. Sorry about that. We're not done. Okay. Finish my voice. Question 3. All right, so now 3.5, it says the soft ball is replaced by a very hard ball. How would this affect the following? Right, only increase, decrease, or remain the same. Luckily for you, you're just writing increase or decrease, not explaining anything. But I see 3.5.2, they want you to explain, so you're not really exempt. So now, if this is a hard ball, the contact time when the ball bounces on the ground, well, the contact time will decrease. Remember, this is a soft ball. As it approaches, once it gets to the ground, it will sort of like deform. It will not be circular anymore. But I don't know if you've seen a ball moving in slow motion as a cricketer hits it or as it bounces on the ground. It deforms. It deforms, therefore it spends more time with the ground. The contact time has increased. Okay, but now if it's a hard ball, oh no. Think about a tennis ball versus a golf ball. A golf ball would actually bounce quite high and spend less time with the ground. Therefore, if that ball hits you, it's gonna hurt because it's gonna come with its force. And because the contact time has been decreased, that force will be still high. It's gonna hurt. Okay, so the harder it is, the less contact time it has with the ground. So it will decrease. Now 3.5.2, the height of the ball after it strikes the ground. Okay, contact time has decreased, force is greater, and if the force is great, it means the height will be increased. Okay, it will go up. All right, so you won't get it. The height then won't be at 0,9. probably be 1 comma something, 2 if you may. So the height of the ball would have increased. And why? That's because we have less contact time with the ground and a higher force that propels it upward, higher. Okay, and that is it, I hope, for 3 point. Yeah, question 3. Let me go get some water, take a break, and we'll see you next time. Hello everyone, and welcome back to MV Tutors. Soon I'll be looking at question 4 with you guys. Please don't forget to like our videos as well as subscribe to our channel. And thank you for tuning in. All right, so we're going to do question 4. Ball X with a mass of 50 gram and ball Y with a mass twice that of X are supported by long strings from a ceiling as shown in the diagram below. So what I'm going to do, I'm just going to say we have ball X and we have ball Y. So what do we know about the mass of ball X? The mass is 50 grams. Remember that the SI unit for mass is actually kilograms. So we're going to say 50 divided by 1,000 and we get 0.05 kilograms. And they say that Y is twice X. Okay, so the mass then becomes 0.1 kilograms. Do we know anything about the velocities? Yes, we do. And X actually is towards the right. Y velocity is towards the left. So I will take the direction of right as positive. Okay, so our initial velocity then for ball X would be 4.5 meters per second, whereas for Y it would be negative 2.8 meters per second. Okay, so that's all we know for now. Now it says the balls are each pulled back and released so that they move towards each other. When the balls collide at the position shown in the diagram above, the strings are vertical and then the balls rebound in opposite directions. So we had X going positive and then negative, Y going negative and then positive. All right, so the velocity of ball X after the collision is 2.1 meters per second to the left, so it's negative. We don't know about the final velocity of Y. Okay, so ignore all effects of friction. Now let's see. It says, state the principle of conservation of linear momentum. Okay, this is where I don't really write down the definition. I'm just going to say it and then you are going to write it down. Okay, so basically it would be the total linear momentum in a closed system. It's important that it is a closed or isolated system. So the total linear momentum in an isolated system remains constant. Okay, I'm not going to write all of that down. We'll go to 4.2. So it says calculate the velocity of ball Y immediately after the collision. Okay, so we know, like we said, they came together and then they rebounded. Okay, so whatever value we're going to calculate for Y should be positive because it's going to go to the right. So let's see. According to our definition, so we have total momentum, or the sum of the momentum before the collision, is equal to the sum of the momentum after the collision. Okay, so basically we have the mass of X and the velocity of X. Okay, let's rather do this, plus the mass of Y times the velocity of Y, and we're gonna say this is before. And the same thing, mass of X, velocity of X, plus mass of Y times velocity of Y after. So what did we have? The mass remains the same for X, which is 0.05. The velocity is 4.5, positive 4.5. The mass of Y is 0.1, and we have negative 2.8 initially. Okay, the mass of X is still the same, nothing happened to it, but the velocity now is negative 2.1, and the mass of Y still 0.1. We are now looking for the velocity of Y finally. Okay, so now, oh gosh, but but I'm closing my phone. And now here it is showing me flames. Okay, so now let us calculate. With our calculators out, we're going to say 0.05. 0.05 multiplied by 4.5 minus 0.1 multiplied by 2.8, because we already incorporated the minus. And then we're going to add, because the 0.05 times a negative gives you negative, but if you take that negative to the other side, it then becomes a positive. So we're going to have 0.05 multiplied by 2.1. Okay, this is now maths. All right, we are cool with the maths part. Okay, so we have 0.05, and that is equal to 0.1, and we have our y velocity final, which is what we're looking for, right? The velocity of ball y after the collision. So the velocity of ball y after the collision is equal to 0.05 divided by 0.1, which then becomes 0.5. And this is meters per second. What am I writing? Meters per second. Yes, I was correct. And this is to the right because it's a positive answer. And that was a nice 5 marks. Okay, now 4.3 asks, is the collision elastic or inelastic? What is the test for elasticity? Also, it says explain the answer by means of suitable calculations. Another 5 marks. So for elasticity, we know that the sum of the kinetic energy before must be equal to the sum of the kinetic energy after. If it's not, then we are not having an elastic collision. So this is now EK before, and the sum of kinetic energy after. Okay, we're going to work that out. So now, kinetic energy, remember the equation, it's half mv squared. So we're going to start half m for the x. Yes, so mx and then v squared. Okay, so v initial for x squared, and then we have half my v initial squared. Okay, we're going to work that out. And then we have half, again, the mass of x v final squared plus half my v final squared. So we know the velocities now. Okay, so we have half times 0.05. The initial velocity, I forgot. Let's just look at our sketch over here. It's 4.5 positive, but it doesn't matter because we're squaring it either way. And then for y, we had 0.1. Our initial velocity was negative 2.8, but we're squaring it. And then here we have half 0.05. Final velocity was negative 2.1 squared plus half 0.1. Final velocity we calculated was 0.5, right? Okay. 0.5 squared. Okay, now let us work everything out. So 0.5 multiplied by 0.05 multiplied by 4.5 squared plus, I'm going to put everything in the calculator. That can be risky, but I'm looking at time. This is me now making sure that I am working within time. But yeah, that can backfire if you click 0.5 instead of 0.05. Then the whole answer is wrong. So we have 0.898. That is 0.9 essentially. and kinetic energy, so that is joules. All right. Now I have 0.5 times 0.05 times negative 2.1. Don't really have to put the negative, but I'll just put it. Okay, and then we have 0.5 times 0.1, and we have 0.5. Okay, and now that is 0.12 joules. All right, the question was, is this collision elastic or inelastic? We can see that the sum of the kinetic energy before is not equal to the sum of the kinetic energy after. Therefore, the collision is it with one L, with two L's. Therefore, the collision is inelastic. Okay, what is the question? Collision inelastic or elastic? It's inelastic. Explain the answer by means of a suitable calculation. We showed it. Kinetic energy before is not equal to the kinetic energy after. And we are done. I think that was also a nice 5 marks. I hope I'm not alone. Okay, so that is that. All right, we're at the last question, 4.4. So ball X and Y are replaced by two identical balls. Okay, if they're identical, it means their mass is the same, unlike X and Y, where Y was twice that of X. Now, how would this affect the conservation of the momentum of the system if the initial velocities remain the same? So now they have the same mass, and now they have the same velocity, with X going in one direction, going to the right, Y going to the left. Okay, so the total momentum before, the sum of the momentum before, will be equal to 0. So going back to our definition in 4.1, what would happen? How would this affect the conservation of momentum of the system? In all honesty, if I had to choose between increase, decrease, or remain the same, the answer would be it would remain the same. Okay? And why is that? Remember that we have an isolated system, okay, or a closed system, first and foremost. So we have an isolated system, and we know that there's conservation of linear momentum. Okay, so the system would remain isolated. Therefore, your momentum before, the sum of your momentum before would be equal to the sum of the momentum afterwards. Okay, and that pretty much sums up the answer. Okay, it remains the same in isolated system, meaning that it is conserved, so the momentum before is equal to the momentum afterwards. And we are done finally with question 4. So we'll see you next time. Hello everyone, and welcome back to MV Tutors, and we're going to continue with question 5. I hope you're all doing good, and please don't forget to like our videos as well as subscribe to our channel. Okay, so let us begin. Question 5. So a ball of mass 0.03 kilograms moves along a curved track as shown in the diagram below. Okay, so you can see it's going down, it's gonna hit a wall, and let's read what they're talking about. Okay, the speed of the ball is v when it is at point A at a height of 0.3 meters, 0.31 meters. The ball moves down the frictionless track and collides with a vertical wall at point B. The kinetic energy of the ball just before the collision with the wall is 0.12 joules. And after the collision, the ball rebounds up the track. Ignore all frictional forces. Okay, so let's start with 5.1. It's a theory question. And it says, state the principle of conservation of mechanical energy. Okay, so I'm not really going to write it down, but we're just going to summarize it quickly. And that would basically be the total mechanical energy in an isolated system will remain constant. Okay, and there you get your 2 marks. Now it says calculate the speed v of the ball at point A. All right, so what do we know at point A? We know that we have some potential energy, right? And because this thing is moving, there is some kinetic energy as well. So let's then use the formula that we know, total mechanical energy, and yeah, and let's calculate the speed. All right. Sorry, so basically we're going to get the potential energy and the kinetic energy at point A, and basically that'll be equal to the potential energy and kinetic energy at point B. Now, what is the potential energy at point A? We know that that is mass times gravitational acceleration times height at A, and the kinetic energy half mv squared at A, and then same thing, mass times gravitational acceleration times height at point B plus half mv squared at point B. Now we know that the mass is 0.03, they gave it to us. Gravitational acceleration 9.8, it's a constant, and the height is 0.31. And at point A, we know that the velocity is v, which is what we're looking for, right? So we're going to say half times the mass, 0.03, and the velocity, which is what we're looking for. Potential energy at B will be 0, right? Because the height there is 0. So I'm just going to say mg times 0. I'm running out of space. So I have half. And then what is the kinetic energy just before the collision with the wall is 0.12. Okay, so we don't really need to write that down. We can just go straight to say 0.12. Okay, so our only unknown in this case is our velocity. So we're going to say velocity squared at A is 0.12 minus 0.03 times 9.8 times 0.31, and that is all divided by half times 0.03, and we can square both sides. This can be dangerous when you just write everything all at once and put it all in the calculator. I think sometimes it's best if we yeah, sorry, I have a tutorial session soon. So yes, it's best if we just calculate step by step, or if you're like me, risking it all, you're just gonna put everything under the square root and hope for the best. So 0.12 minus 0.03 multiplied by 9.8. I hope the preparations for the prelims are going well. Please do not leave them for the last minute. Start preparing now before the work overwhelms you. Okay, so now we see that we have a velocity of 1.387, so we can just say 1.39 meters per second. All right, 5.3. The change in momentum of the ball due to the collision with the wall is 0.096. Okay, let's just write down that information for ourselves. Change in momentum 0.096 kilogram meters per second, and the ball is in contact with the wall for a time of 0.02 seconds. Now, for the ball hitting the wall, calculate the speed immediately after the collision. So you have your ball going towards the wall, right, with some velocity, and then it gets to the wall and then it rebounds, right? So what they're looking for is this rebounding velocity. Okay, our final velocity. And do we have our initial velocity? No, but we can calculate it because they told us that the kinetic energy of the ball just before the collision with the wall is 0.12 joules. Okay, so we can use that information to be able to calculate our initial velocity. Okay, and so we're going to say kinetic energy is equal to half mass times velocity squared. So velocity squared is equal to our kinetic energy divided by half times mass, and we can square root both sides. So basically our velocity, remember this is initial velocity that we're calculating, okay? And we're choosing right as the positive. The rebounding velocity, which is final velocity, that one we're expecting it to be negative because it's going in the opposite direction. So our initial velocity will be equal to the kinetic energy, which was given at 0.12. Then we have a half times 0.03 kilograms. And we're square rooting everything. Okay, so getting out our calculator, we have 0.12, a half, 0.03. Okay, we have 2 root 2. Please save that answer. Do not get rid of it as now. So 2.83 meters per second. Okay, cool. Now, we're not done. We just got the initial velocity. They mentioned change in momentum. What is the change in momentum? Basically, it's your mass where you have your final velocity minus your initial velocity. And for your mass, we have 0.03. Final velocity is what we're looking for. Initial velocity is 2.83. All right. And our change in potential energy, in momentum, is 0.096. Okay. And in this case, then, yeah, like I've said, we're going to expect our answer to be a negative. And so in this case, because we have our ball rebounding, our change in momentum, we can take it as negative at that point. So we have negative 0.096 divided by 0.03 plus the 2.83 will give us our final velocity, okay, or the speed immediately after the collision. Because they are looking for speed, once we get this answer, we need to write down the magnitude actually. Okay, so we have negative 0.096 divided by 0.03 plus 2, oh, look at me. I should be using the answer from the previous question. So I have negative 0.37 meters per second. That is the velocity, but the speed is actually 0.37 meters per second. It is the magnitude. Remember, speed is magnitude, velocity is a vector. So that is immediately after the collision. And then now I have run out of pages. Let me just insert. So let us go now to 5.3.2. Okay. Now it looks, we're looking for calculating the magnitude of the average force on the wall. Okay, so remember your force calculation. Your net force is equal to your change in momentum over your change in time. Okay, and so we do have our change in momentum, which is given as 0.096, and our change in time is 0.02 seconds, and therefore if we work that out, 0.096 divided by 0.02, and that gives us 4.8 Newton. Okay, average force. Why did I write net force? Average, average, average. Do they have this formula in your formula sheet, or is it something that you have to know? Work, energy, and power. Oh yes, so we have force there. F net delta T is equal to, yeah, so we can have F net. But here we're looking for our average force. Okay, but yeah, anyway, F net, F average, the formula says net, use it. So 4.8 Newton is what we got. And that is it for question 5. See you guys next time. Hello everyone and welcome back to MV Tutors. I'm Tolo and we are going to do question 6 right now. All right, so let's get right to it. Please don't forget to like our videos, subscribe to our channel. Thank you for your comments. Really appreciate them. Yeah. Okay, so it says the diagram below shows a fairground carriage moving at a constant speed. Let me just make this a bit smaller. Moving at a constant speed of 9.5 meters per second over a frictionless surface, right? The total mass of the people in the carriage is 600 kilograms. The carriage moves up a slope inclined at 30 degrees to the horizontal. The carriage comes to a stop after traveling up the rough slope to a vertical height of 4.1 meters at point C. All right. I wasn't really focused much on what I was reading. I was just focusing on the noise that's behind me. Sorry. Okay, let's just get to it. So 6.1, state the work energy theorem in words. Okay. Sometimes if you cannot remember the definitions, try to look at the formulas and try to formulate the theory from there. Okay, so the one that resonates would be the network being equal to the change in kinetic energy. But let's go back. So the work energy theorem states, okay, so basically work done by the net force is equal to the change in the object's kinetic energy. Okay, remember net, the work done by a net force is equal to the change in the kinetic, it's equal to the change in the object's kinetic energy. Yes. 6.2, calculate the kinetic energy of the carriageway and passengers as they reach point B. So they've already told you from the sketch, you can see that they are going or moving at a constant speed of 9.5 meters per second, right? So as they approach B, it's still the same constant speed. It will be that as it goes higher up the slope that it starts decreasing, okay? So yeah. Okay, but yeah, unless if there's a motor that's keeping it going at the same, like on cruise control, no matter whether you're going up or down, it's gonna maintain the velocity or the speed. But yes, so now our kinetic energy, which is half mass times velocity squared, and we're calculating the kinetic energy. So we know that the mass of both the carriage and the people is 600 kilograms. And the velocity there is 9.5 meters per second. And you're going to square all of that. And then we're going to calculate and see what the answer is. Ooh, what happened now? Ah, technology. Okay, there we are. We're back. So let's get out the calculator. And we have 0.5 times 600 times 9.5 squared, and we get the energy of 27. You can write it in kilojoules if you want to. I'm just going to keep it to joules. 27,075 joules. All right. And then it says in 6.3, draw a labeled free body diagram of all the forces that act on the carriage while moving up the slope. All right. Did they say something about frictionless some way? Yes, it moves over a frictionless surface. Oh, but now it's traveling up a rough slope. Okay, so we know somewhere we need to have our friction. Okay, so anyway, this is our, it represents our carriage, right? And the people in it. What is always acting downwards would be your gravitational force, your weight, if you may. What always acts perpendicular to the surface will be your normal force, right? And then because it's moving upwards, your friction will oppose the motion, right? So it will act downwards, making it a smaller value, nothing like hectic. What you can do is also resolve. Let me use a different color pen. Resolve. You don't have to. Honestly, you don't have to, but you can resolve your weight or your gravitational force in its x and y components. Okay. So we have the 30 degrees. Okay. So this component will be Fg perpendicular to the surface. Okay, where it is actually Fg cos theta. However way you prefer writing it. And then you're gonna have yeah, Fg sine theta, or your Fg parallel component. It's up to you really how you want to put it, but either works. You could have just stuck to the blue lines that I've put there, vector lines, or you could put Fg in its x and y components. It's really up to you, but 3 marks, 3 vectors, that's good to go. Okay, and now 6,4. So it says use energy principles and calculate the frictional force between points B and C. Now at that point, you know that friction is a non-conservative force, okay? And as a result, you can then use this formula in your formula sheet, where you have, is it there? Yes, it's there. The work done by a non-conservative force is equal to the change in kinetic energy plus the change in potential energy. Okay, can use that. All right. Okay, and that's between points B and C. All right. Frictional force, and that is a nice 5 marks. So we will be working here. So basically, the non-conservative force is the work done by friction. Okay, and you have your change in kinetic energy and your change in potential energy. So basically, you have half m velocity at B squared minus velocity at A squared plus mass times gravitational acceleration, the height at, wait, between B and C. Yes, I'm thinking A and B. Okay, between B and C. So the height at C minus the height at B. Okay, now let's plug in the values. So we have, I think I'm going to need space. So let's, no, actually, we also need to write stuff on the left side. So we have half times the mass, the velocity at C. Remember they said the carriage comes to a stop after traveling up the rough slope to a vertical height of 4,1 meters at point C. So it stops at point C, so that's 0, and at B we have 9,5 meters, and we're going to square that, meters per second. Okay, the mass 600, gravitational acceleration is 9,8, the height at C is 4,1, the height at B is 0. Now what happens to the work done by the friction force, our non-conservative force? Remember, work done is force times the distance that it travels and cos theta, right? So it's going up a slope. If this were to be B and that is C, we are looking, this is our delta X at the moment, okay? But remember our height at C is 4,1. and we're looking for our hypotenuse, all right? And what do we know? This is 30 degrees. I'm just going to put a dot there because my pen is so thick, you won't see the 30. So basically, our delta x at this point, if I am looking at, opposite this angle is 4,1, and then we're looking for our hypotenuse. So basically, sine 30 would be equal to 4,1 over or our h. Before I put 4,1, let me say it's our height, 4,1 divided by our hypotenuse. Okay, should I call that delta x? Well, it is our x since we put everything. This is our new x, and that's y. So that is our x. We can say that's delta x. So what will delta x be equal to? It will be equal to, ultimately, delta x would be equal to h over sine 30. Okay, so we can write that down. So we have our friction force, which is what we're looking for, remember. Delta x is h over sine 30. We'll put in the values. And cos theta. Okay, so the friction, where is it acting? Is it acting where the carriage is going? Is it acting in the opposite direction? It's acting in the opposite direction. That's friction for you. So we're going to use cos 180 degrees. Now when we simplify things, we have our friction force. Our height is 4,1. Sine 30 degrees is a half, your special angle. Cos 180 is -1. And then we have a half times half times 600 times negative. We've calculated this before though, but it was just positive when we calculated it. So we have negative 27,075 joules plus, so you have your 600 times 9,8 times 4,1, and that is 24,108 joules. Okay, so 24 minus 27,075, that is negative 2,967 divided by negative, I'm dividing by this whole term over here. Okay, the 4,1 divided by 0,5, that's what, 8,2. Or should we not calculate in our heads? Let's just use the calculator just in case. Let's see. Yeah, man, it's divided by half, which is like multiplied by 2. So anyway, our friction force then becomes 2,967 divided by the answer, which is 361,83 Newton. Oh, it's getting dark in this place. Okay, so yeah, that is your 5 marks. I think it was a nice 5 marks. What do you think? Okay, so that's 6.4. And now 6.5. Ooh, this question was loaded. Now we're dealing with tractors over here. So now it says a tractor, a small tractor, is rated 9 kilowatts. Okay, so that's power, right? 9 kilowatts. And pulls an empty carriage across the ground at a constant speed with a horizontal force of 300 Newton. Okay, constant speed. Now, let us define a non-conservative force. Okay, we already said in the previous question that friction is a non-conservative force. And what do we know about a non-conservative force? 6.5.1. So it's basically a force for which work done in moving an object from point A to point B is not dependent. It is dependent. If it's non-conservative, it means it is dependent on the path taken. Think about the friction. Friction is dependent on the path taken. But a conservative force, like maybe gravitational force, it is not dependent on the path taken. Okay, so yeah, keyword to note here. Okay, it is basically the force for which work done in moving an object from point A to B or from one point to another is dependent on the path taken. Sometimes I forget, like, is it dependent or not dependent? But non-conservative is dependent, whereas a conservative force is not dependent. Okay, so yeah, that's basically that. Depends on the path taken. Now 6.5.2. Trying to finish this question before I am in complete darkness. So 6.5.2. Calculate the time that it would take the tractor to tow the empty carriage at a distance of 850. We have our force. Now they've given us the distance of 850 and we're looking for the time. Okay, so I suggest we go to the formula sheet, go have a look at which formula would best be suitable with power, work, time, and all of that. So you can see here, just make that a bit bigger. We have our formula where power is equal to work, yeah, the rate at which work is done, right? And you also have the formula where the average power, but yeah, here we're not dealing with average power. Okay, so we know that we have power is equal to work done per unit time, the rate at which work is done, and we also know that work is equal to our force delta x cos theta. Okay, so we can actually then put it like this. And what do we know? Do we have power? Yes. We have power. We have force. We have the distance. And what we need is time. Let's go back to our question. Okay. Now let's substitute what we know. The power is 9 kilowatts. Power, we normally put it in terms of watts. So we'll have 9,000. Our force is 300 Newton. Okay. Delta X is 850 meters. Cos theta, so it's moving that way. The force is that way. We can say our theta is 0 in this case. So cos 0, which will give us 0 degrees, it will give us 1. And our unknown is delta t. So delta t is all of that divided by 9,000. So let's just calculate. 300 multiplied by 850 multiplied by 1 divided by 9,000 is equal to 28.33 seconds. Okay. And then it says 6.5.3. How would the time change if a tractor with a greater power output was used? Let's go back to our power formula. Power, work over delta t, work, the rate at which work is done. So how would the time change if a tractor with a greater power output was used? Okay, so the greater the power, because power in this case is directly proportional to the work done. So the higher or the greater the work done, the higher your power output, the lower the time it takes, right? So would it increase, decrease, remain the same? Explain your answer. Okay, so in this case, your time factor, or how would it change how would the time change? Your time would decrease. Okay, first of all. Okay, and what would we say about that? Well, basically the work done on the carriage stays the same. Okay, and we know that power and time are inversely proportional. So increasing your power will basically decrease your time. Okay, but the work remains the same because what you're changing is your power output. All right, so I would leave it at that. Work stays the same, increasing your power, time has to definitely decrease. And that's it. Okay, so that's it for question 6. Let there be light. And I hope that also with you, the light bulb was switching, especially if this topic is a bit of a challenge. But thank you for tuning in. I don't know if you can still see me, but yeah, enjoy the rest of your day. Hello everyone and welcome to MV Tutors. I'm Solo and we are continuing with the physics paper written in June, right? And I hope that preparations are going well for your physics and chemistry papers. Okay, so the maths has already been written. So yeah, two charged spheres, A and B, are placed 15 centimeters apart in a vacuum. I am immediately going to take that 15 centimeters and turn it into meters, okay, because we work with meters. So that's going to be 0.15 meters. Sphere A has a charge of 3 picocoulomb, and sphere B has an unknown positive charge. Okay, at least they told us if it's positive or negative. Now the arrangement is illustrated in the diagram below. Okay, while we're at it, please don't forget to like our videos and subscribe to our channel. So now point P lies on the line joining the charged spheres at a distance 5 centimeters from sphere A. Okay, so 5 centimeters will be 0.05 meters. Remember, 100 centimeters is equal to 1 meter. But you already know that, right? Yeah, so hence, yeah. Anyway, 7.1, this is the theory portion, which I'm not really going to write down. Just going to help you say it. But it says, describe an electric field. So what is an electric field? Basically, it's an area or a region in which an electric charge experiences a force. Okay, so whatever region or area that you have, this is your region or your area where an electric charge experiences a force. Okay, let me just erase that. Okay, and that's 2 marks. Region where an electric charge experiences a force. Now 7.2, the net electric field strength at point P is 0. Okay, calculate the charge of sphere B. Okay, so if you've forgotten the formula, you have the formula sheet with you, so we can go have a look. Electric field strength, and what do we have here? Okay, so E is the electric field strength. We're not calculating force, it's just E. Okay, and it's basically, you're going to calculate the sum of all that we have there. So the sum of the electric field strength, all right, which is our constant K over R squared. So yeah, and what is K? That should be 9 times 10 to the power 9. Yeah, so let's just go back up again and have a look. Okay, the electric field strength at point P, 0, calculate the charge of sphere B. So we're going to look at that for A, and we're going to look at that for B, because this is the sum. Okay, and they told us that it is 0. So from the onset, we can then put E as 0. Okay, and our K, 9 times 10 to the power 9, and the charge at A is 3 picocoulomb. So 3 times 10 to the power 12, negative 12, negative, 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 negative 12. And before we even go further, we are taking write as positive. Okay, so if you look at A, just going to sketch. So we have A here. And if you were to draw the field lines, they would be going outward because it's positive, right? So this is A. Then you have P in the middle. Well, not really in the middle. And then you have B towards the end. But let me just, this is really not to scale. So B as well. We have its electric field lines. It's also positive. So they'll be going out. Now, in relation to P, this is what we are interested in. We are interested in, because we want to determine what the sign is. Okay, so this is what we are interested in. And if we've chosen right as positive, it means left will be negative. Okay, so here we have our positive. Okay, and r squared, so 5 centimeters. We already said that 5 centimeters is equal to 0.05 meters, and that's squared. And now we get to B. So 9 times 10 to the power 9. And the charge there, it'll be negative. Okay, let me just put a negative in front once. Negative, why? Because this is going to the left, and that's negative. That is going to the right, and that's positive. So it'll be negative. The charge is what we're looking for, right? And the distance then from B to P should be 10 centimeters, which is 0.1 meters squared. Okay, so I hope you can see how we get to determine whether the charge is negative or positive. Just draw out there the electric field lines. That's the easy part. Then you can see in relation to what you're looking for. Is it going to the left? Is it going to the right? And it will make the signs a bit easy. Okay, so now we're going to do some math gymnastics in order to determine what the charge for B is. Okay, so I'm just going to take this to the other side. 9 times 10. Let me just put this in a bubble. It's just for illustration purposes. Then multiply by 3 times 10 to the power negative 12 all over 0.05, and that is squared. And then I'm gonna multiply by the 0.1 squared. I hope you can see what I'm doing. 9 times 10 to the power 9, and we are left with the charge for B. So I took this entire sum to the side, and then I multiplied by the denominator and divided by the numerator, and the negatives will cancel. Okay, so everything here will be negative. All right, and the negative sign is also left there in case you're wondering where the negatives went. And then now we can calculate the charge of B. Okay, so let's just take out the calculator and calculate this whole sum. If you want to, you can take it step by step. I prefer just writing everything. Sometimes that is not really ideal, especially if you start getting weird answers. Okay, so 0.05 squared, and we are multiplying by 0.1 squared all over 9 times 10 to the power 9. Wait, is it a positive 9 or a negative 9? That looks too big. Oh, it is a positive 9. Okay, just making sure. There's the calculator. And then we get 1,2. So the charge at B, which is positive, is 1,2 times 10 to the power negative 11. If you want to work with the picometer, okay, we're simply going to take the comma to the other side, and that's basically equal to 12 times 10 to the power negative 12, not 11. We're trying to get it to picometers. Actually, let me just say 12, not picometers, sorry, picocoulomb. Ooh, 12 picocoulomb. Okay, so yeah, that is how you would do that. Okay, and then we are now at 7.3. All right. Another theory question. So it says, state Coulomb's law in words. So what is Coulomb's law? Actually, if you have forgotten Coulomb's law, check out this formula, and the formula will help you to put something in words. Okay, where you're like, okay, I see what the formula is saying. Let me try to tell a story here. Okay. All right. Okay. So what is going on here? This is where we use Coulomb's law. If ever you forget any theory question, please try to go to the formula if you remember, because you normally state the law before you use the formula, and then from the formula try to explain what really is going on there. Okay, so basically Coulomb's law says the magnitude of the electrostatic force, okay, exerted by one point charge to the other is directly proportional to the product. Okay, you see Q1 times Q2, directly proportional to the product of the magnitude of the charges, and inversely proportional to the square of the distance between them. Okay, I hope that makes sense. Let's repeat that again. So the electrostatic force between 2-point charges is equal to the product of the product of the magnitude of each of the charges, and inversely proportional to the square of the distance between those charges. That's that. And then 7.4, charge B is replaced by a negative charge of magnitude negative 12 picocoulomb. All right, calculate the magnitude of the electrostatic force between charged spheres A and B. All right, so now when you work this out, you're wondering, am I going to use a negative? Remember in our definition, we said that the electrostatic force is equal to, electrostatic force between two charges is equal to the product of the magnitude. So in this case, whether it's negative 12 picocoulomb or positive, it doesn't matter. It doesn't really influence our answer. So the force then, we have 9 times 10 to the power 9. The charge at A, okay, let's rather put A and B. So charge at A is 3 picocoulomb, so times 10 to the power negative 12. And charge at B is 12 picocoulomb, 10 to the power negative 12. And that is all divided by the distance between the charges, right? The square of the distance between the charges, which is 15 centimeters. But in this case, we're going to write 0.15 meters. And we're going to square all of that. Okay. And now let us get to calculating. Okay, so we have 9 times 10 to the power 9 and multiplied by 3 times 10 to the power negative 12 and multiplied by 12 times 10 to the power negative 12 all over 0.15 squared. Okay, and that is equal to, so this is the force, so units must be in Newton. So that is equal to 1,44 times 10 to the power negative 11 Newton. Okay. And then, lastly, we're at 7.5. Okay, so this is a nice short question. 7.5, how would the magnitude of the force calculated in 7.4 be affected if the distance between the charges is decreased? Remember we said in our definition of Coulomb's law that the force, electrostatic force between two charges, is inversely proportional to the square of the distance between the charges. Okay, so now if the distance is decreased, so if you're going to decrease the distance, then the force, what would happen to the force calculated? It would have to increase. Okay, if you're going to make this value over here, 0.15, a lot smaller, still have the, yeah. If you're going to make it smaller, let's say 0.1 instead of 0.15. So previously we had 1.44 times 10 to the negative 11. Now we're going to have 3.24. Okay, so you see that it increases. So 7.5, the force would increase. And it goes back to the definition. So explain the answer. Seeing that, or because the force is inversely proportional, electrostatic force between two between two charges is inversely proportional to the square of the distance between the two charges. All right, so it would increase because of that, the inversely proportional statement. Okay, yeah, so I said it. And thank you for tuning in. That was a nice short question. And yeah, see you again next time. Hello everyone and welcome back to MV Tutors. I'm Solo and I'll be looking at question 8 with you guys. I hope you're good. All right, let's get to it. So an experiment is conducted to investigate the relationship between the force experienced by a charge if the electric field strength is kept constant. Okay, so E is kept constant. The table of results is given below. So the force, as you increase the force, you can see that the charge also increases. If you go back to question 7, you know that the force is directly proportional to the product of the charges, right? But yeah, if you increase the charge, the force will increase. So this is what is expected. You can see that they are directly proportional, even with that graph of force versus charge. Okay, positively linear. Okay, so now 8.1, it says define the electric field at a point. I repeat, if ever you forget to define certain things that they ask, please make sure you know the formula at least. Okay, so basically, you'll be using this formula to define the electric field at a point. Okay, and what is that exactly? Because I see force per unit charge. Okay, so basically, the electric field at a point is the electrostatic force, okay, experienced per unit positive charge. I think that the main thing to take out of this is per unit positive charge. Please don't forget the positive part, okay? So yes, the electric field at a point is equal to the electrostatic force electrostatic force experienced per unit positive charge, okay, placed at that point. So don't forget, like I said, don't forget the positive portion of it. All right, in 8.2, give the relationship between force and charge. Okay, we've already spoken briefly about it, but basically we can see that the force is directly proportional to the charge, and you can see that they basically increase at the same ratio. As the charge increases, so does the force. Okay, so yeah, it's a straight line, it's going up, positive gradient. So yeah, that's how you would explain it. Okay, and then 8.3.1 now says use the information above to calculate the gradient of the graph. Okay, so the gradient. We know that the gradient is equal to delta y over delta x. Let's just make this a little bit bigger so that we can see what is going on. All right, so we're going to just choose two values that should give you the same. It doesn't matter where you take it. The gradient should be the same because this is a straight line. It's not like a curve. Okay, so I'm going to take at the origin. Okay, now what did I do? Oh, gosh. Okay, so basically at the origin. Ooh. Yeah, never mind. So at the origin, and then choose another point that is obvious. because everything else, I think I'm going to go between 10 and 20. That looks like it's directly at 15. So yeah, and then also at 0, 1. So delta y, so I'm going to go 0, 1 minus 0, okay, 0, 1 Newton. And then over delta x, I'm also going to go 15 nanocoulomb. So 15 times 10 to the power negative 9 minus 0. And let's see what that gives us. So we have 0, 1 all over 15 times 10 to the negative 9. Okay, that gives us a very big gradient. So let's see, 3, 6, so it's like 6, 6, 6, 6, 6, 6, 6, 6, 7. Well, we have Newton per coulomb. Okay, so Newton per coulomb. But let us make that, so it will be 6,67 mega. Or let's just say times 10 to the power 6. There are too many things going on. If I put mega and mega and then Newton per coulomb, it might just be a little bit of a mess. So let's just leave it there. So that's the gradient of the graph, okay? Newton per coulomb. And you can see this is exactly what E is, okay? Newton per charge. Yeah, so 8.3.2. Let's just take it up. Now it says use the information above and calculate the value of x. So we have our gradient. How many marks is this? If it's a lot of marks, we might have to get an equation and you know, so value of x. So we're looking for the force, or maybe not. We have the gradient. We're looking for the force. Actually, guys, I didn't see. I forgot about this table. I forgot about this table. I should have actually looked at it and just used 0, 1, and then we have 15,2. Okay, let's just recalculate that quickly. So there I was straining myself for nothing, whereas I could have just looked at the table. Okay. If they have given you the values and you go and decide to use your own, ooh, that is very dangerous. So we have 6, 5, 7, 8, 9, 4, 7, 3, 6, 8. At least we have time to rectify our errors, my error in this case. So 6, 5, 8 times 10 to the power 6. Okay, cool. More accurate now. Yeah, so now it says determine the value of x. What would you do in that regard? You have your gradient. You can go and use the gradient formula again. The only thing that would be unknown is x. Okay, so we can then say the gradient. I'm just going to say m for gradient is equal to x. No, force, yes. X minus 0. I'm going to take the origin. And then we have 63, 8 times 10 to the power negative 9 minus 0. Okay, and the gradient, we had 6, 5, 8 times 10 to the power 6. I'm going to multiply by 63, 8 times 10 to the power negative 9, and that will be equal to x. And if we put that into the calculator, we're basically going to use this value that we got over here multiplied by 63, 8 times 10 to the power negative 9. Does that make sense? Yes. If we had 0, 0.35, 0, 0.42 makes sense. Okay. So x is equal to 0, 0.42, and that would be Newton. Question 8.4. Now it says, sketch the electric field pattern around the charge if it had been a negative charge. Guys, this is a nice question to have. Hopefully your prelims are this nice, but this was June. Okay, prelims are going to be a bit harder, but you got this, right? Okay, so anyway, if it had been a negative charge, you draw your field lines. And you know with the negative charge, the field lines go inside. And how many marks is that? Hopefully 2 marks, ne? 3. Wow, okay, they were being very generous. All right, and that is it for question 8. Thank you for tuning in. Hello everyone and welcome back to LV Tutors. We are finishing off this question finally after a very long time. And let's get right to it. So, one way to tell if a mosquito is about to bite is to listen to the Doppler effect of the sound emitted by the mosquito as it is flying. And it is very irritating. You can hear it. Summer is approaching and we're like, the mosquitoes are coming, the flies are coming. So the buzzing of a mosquito's wings emits sound at a frequency of 1050 hertz. The speed of sound is 330 meters per second in air. Okay. Guys, I always see this question. Please make sure you know the definition of Doppler effect because, yeah, question 6 normally for your papers, this was just a June paper, but for your finals and your prelims, question 6 is normally the Doppler effect. They almost always ask this question, so please make sure you know it. So, state the Doppler effect for sound in words. So basically, when you have a change in observed frequency, okay, of the sound detected by a listener, all right, because the sound source and the listener have different velocities relative to the medium of sound propagation. Yeah, so this was a very formal definition as it is written in the textbook. So basically, because you have the source of the sound and you have the listener, and because they have different velocities, there'll be a change in observed frequency. That's basically what the Doppler effect is. You can write it in a simpler version or simpler form. You can have a look at our Doppler effect lesson on our playlist for physics. But yeah, that's 2 marks. Okay, so the change in the observed frequency of the sound detected by a listener. Okay, because the sound source and the listener have different velocities relative to the medium of the sound propagation. It's basically very formalized. I don't like formalized definitions. If you can explain it simpler, please do it. Yeah. 9.1.2. So if you hear a frequency, okay, of 1034 hertz, does this mean that the mosquito is coming in for a landing or that it has just bitten you and it is flying away? Okay, remember it emits 1050 hertz. Okay, and we are now talking about 1034 hertz. Okay, so what does that mean? It is a lower frequency that you are hearing. And if it's a lower frequency, think about it. When something is coming towards you, you hear a higher, there's a higher frequency. Okay, the waves are much bigger coming to you. But when they're moving away, you get a lower frequency. Okay, so in this case, it's moving away. So it has just bitten you, unfortunately. And it is flying away. So moving away from you. Or in this case, flying away from you. Flying away from you. And why is that? Give a reason for your answer. That is because the observed frequency, okay, at that point in time is less than the actual frequency, which is the observed frequency is less than the actual frequency. The observed one is 1034 hertz. And the actual one is 1050 hertz. Okay. 9.1.3. Calculate the speed of the mosquito when you hear the frequency of 1034. This is where we go to our formula sheet. Okay, for Doppler effect. Yes, there we have the frequency of the listener. And this is where you need to now decide, do you have a plus or minus? So you have the speed of sound in air, and you have the speed of the listener, which is probably 0 because you're just sitting there still sleeping, minding your own business. And that's the speed of the source. I don't want to use B, I'd rather use S. Okay, and now the frequency of the source. All right, so here whether you use plus minus doesn't really matter because the velocity of the listener is 0. Okay, they're sleeping at this point. But now this speed, okay, which is what we're looking for. At the bottom, at the denominator, are we going to use plus or are we going to use minus? Okay, so in this point in time, we're going to use a plus. And let's go back to our question over there. Okay, so we know that the speed of sound in air is 330 meters per second. And like I said, plus 0 minus 0 doesn't matter. And at the bottom, we have 330 plus, which is what we're looking for now, the speed of the mosquito. And the frequency of the mosquito, when you hear the frequency, so the frequency of the listener is 1034. The frequency of the source is 1050. And now let's get to calculating. Okay, so we're going to have 1034. And we have 330 plus the speed of the listener. So we have 330 times 1050. And then I'm going to divide both sides by 1034. Okay. And so now we have 330 plus the velocity of the source. Ooh, my S. Okay, so we have 330 times 1050 over 1034, and we're going to subtract 330 both sides. So now the speed of that mosquito. Okay, so we have 330 times 1050 all over 1034 minus 330. And we got it then the speed to be 5,1 meters per second. That's quite a lot. But they do move quickly. 5,11. 5,11 meters per second. Ooh, yes, I'm out here recording. I should be going to my doctor right now. Guys, the love we have for you. The Doppler effect has many other uses. Okay, so one of the uses of the Doppler effect is in the field of astronomy. Let's make that a bit bigger. It's in the field of astronomy. Okay, so while studying the stars, a redshift emission is observed. Okay, so is the star moving away from the Earth or towards the Earth? So this is where you do the redshift and the blue shift. And if you know, with the redshift, has a lower frequency but a higher wavelength. So higher wavelength, lower frequency. So is the star moving away from the Earth or towards the Earth? If you have lower frequency, remember, moving away. And then 9.2.2. Another use of the Doppler effect is in the medical field. Okay, give two uses of the Doppler effect for, no, no, give two uses of the Doppler flow meter on humans. Okay, so what can it be then used for? So yes, I'm going to the doctor to see if everything's going well with our baby. So basically, you can use Doppler effect to monitor or measure the fetal heart. Okay, beat. As you can hear, okay, this fetus heartbeat, which is quite fast, faster than a normal grown human being. So yes, it's used for that, just to determine, the heartbeat, is it okay, and all that. And then another one that you can use as well would be to measure the flow of blood. I guess if you want to know the blood pressure, when they wrap that thing around your arm and then pump and pump and pump, and then you start hearing your heartbeat actually when they take your blood pressure, and then the doctor measures that, and yeah, I can tell you if you are good to go or if your blood pressure is high, blood pressure is low. So yeah, that's it from me, guys. Let me go to my appointment and go to work.